electric potential due to a dipole. Last time we discussed electric potential due to a point charge. Okay. So today we'll discuss electric potential due to a dipole. Right? Let us first draw a dipole. Okay. This is a dipole. There are two charges separated by a small distance. Let us say this is minus q, this is. Now there will be two cases. First is when you want to find the potential at axial point, same as we did for the electric field, right? This is a dipole separated by, this is a vector p. What is p? Q into 2a, isn't it? This 2a is the distance between the the two charges, right? Now we want to find electric potential at some point p on the axial line of this dipole. Okay, how can we find that? So let us say this distance from the middle to this point p be some r distance, and each one of these distances is a because the whole is 2a, correct? So it is very easy, right? You will find the potential due to each one of these charges and then simply add them, because the electric potential is a scalar quantity. Okay, so you want to find the potential at this point. The potential at this point will be because of these two charges only, because there are no other charges lying here, right? There is minus q charge, there is plus q charge, and what we will do is we will find the potential due to each one of these charges. So let us find. So let us say this potential is due to the minus q, it is v1. Okay, what is the potential due to a point charge? See, this is still a point charge because there is no some, what is v? 1/4 pi epsilon naught. Tell me, what is the formula due to a point charge?
KQ
1r, right? So kq upon the distance. R means the distance, so distance from p to q will be a plus r, isn't it? From minus q to this p, the distance is r plus this a. Now because of this plus q charge, the potential at point p will be 1/4 pi epsilon naught q by this distance, which will be r minus a, right? Okay, instead of writing this a plus r, you write it as r minus a, sorry, r plus. And you remember that while finding potential, you should put in the charge with sign, right? Because this is not a vector quantity, this is a scalar, right? So potential is a scalar, so you should
Yes.
always write the sign. Now the total potential, what will be the total potential at P? Because since they are scalar, right, so there is nothing to worry about. We can just simply add them, right? I hope you have not forgotten scalars
So
while dealing with vector for so much time, no? Total potential will be V1 plus V2. Scalars we simply add, right? The total, if you want to find the overall, then we simply add. Because all the sign is taken care by already, right? You know,
yeah.
we'll not subtract, we'll add the sign. So V will be 1 by 4 pi epsilon naught minus q by r plus a plus 1 by 4 pi epsilon naught q by r minus a, and you just need to solve it now. So v will be, you can take this common, 1 by 4 pi epsilon naught q, right? And inside you will get minus 1 upon r plus a plus 1 upon r minus a. So if you solve this, what you will get? What will be the LCM? LCM will be the product of the two, r plus a, r minus a, and here you will get minus r plus a plus r plus a. What do you say? Hmm? This is the LCM, right?
Yeah.
So when you want to find this one, you will get r minus a.
Yeah.
So what you will get in the numerator? Just 2a, right? Because r gets cancelled. So q by 4 pi epsilon naught into 2a upon this will be a plus b into a minus b. So a square minus b square, right?
So r square.
Now first you write this q into 2a as the p. Can we write this? Q into 2a is p, right?
Yeah.
And then what we have, 1 by 4 pi epsilon naught was always there upon r square minus a square. This is the potential. Now you need to note one thing. See, this r will generally be very much greater than a, because the distance between the dipoles is very less as compared to this distance. So we can say that r is, this r is much greater than a. R square will always be greater than a square, right? So we can neglect this a square.
Yeah.
So what would the formula become? P upon r square, 1 by 4 pi epsilon naught p by r square, right?
P by square.
This is the final result. You need to remember this. So this is the potential at axial point of a dipole, 1 by 4 pi epsilon naught p by r square, right? Got it? And now you can see this potential is varying inversely with r square. All right?
Yeah.
This is not varying linearly as in case of our point charge, which is 1 by 4 pi epsilon naught q by r. Here v varies inversely with r, right? But here it varies with r square.
No.
This is done. Now the second position we can find the potential on a dipole is at the equatorial point. So let us also do that. So
Okay.
at equatorial points, now let us again draw dipole minus q plus q. Distance is between them is 2a. So this will be a, this will be a. We want to find potential at an equatorial position. Remember, equatorial position is what? What is the equatorial?
In the middle, somewhere.
Yeah, middle perpendicular to this. So any point.
I like the same distance.
Let we let us mark this as P, right? So we want to find potential at this point.
Yeah.
Okay, and let this distance be what? From O to P, let the distance be R, and this distance will become what? If this is R, this is 90 degrees, right?
What is R?
O to P.
Okay. That will be under root square plus R square.
Yeah, that would be under root of
Right.
a square plus r square. Similar, so let's say this a. Similarly for this is r, this is still a, then the same thing. So this will be under root a square plus r square again. So let us find the potential. So again we will find the potential due to each one of these charges at P and then simply add them. So let us find V1 due to minus Q charge. It will be 1 by 4 pi epsilon naught Q. Q is minus Q divided by R square. So the square of this distance, which will be a square plus r square only, because this will get rid of under root when we square.
Yeah.
V2 will be 1 by 4 pi epsilon naught. Charge is plus Q. Distance is again a square plus r square. Now if you add the two to find the resultant, V1 plus V2 is the resultant. See, they both are identical except one is positive and one is negative, so they both will cancel out and hence the result is 0. Okay, so
Yeah.
there will be 0 potential due to a dipole at equatorial points. At all points here there will be 0 potential. Okay,
Okay. Yeah.
so these are the 2 points where we generally find the electric potential. Now there is third case, which is the general case. We will not prove it, I'll just write the formula for you. At any arbitrary point, arbitrary means the point that is neither on the equatorial line, neither, and no, it's also not on the axial point. So for example, if this is a dipole, right, then the
Yeah.
the general point can be something, it can be like here. So this point is also not on the axial line and also not on this equatorial line, right?
Okay.
So this is we call as any arbitrary
Yeah.
point. You want to find the electric potential at this point. Okay. So what we do is
Yeah.
first we first we join this middle to this and call it as R. Okay.
Okay.
And further we call this angle as theta. The angle between the P vector and this R vector. Okay.
Okay.
So what is theta? Let
Yeah.
us write it. Theta is angle between P and R. So I am just writing directly for you the formula because the derivation will not be coming into the exam. So if V is 1 by 4 pi epsilon naught. Okay, this is always there. And here what we have is P cos theta divided by R square. Okay, see this formula. First one, the first the
Okay.
axial point we were getting 1 by 4 pi epsilon naught P by R square, right? So at arbitrary point we have to
Yeah.
add a cos theta, the formula, right? And rest is the same. Okay,
Yeah.
so this is
Yeah.
the formula. You can just write it. Now this formula is valid for any point. You can also use it to find the potential at equatorial and axial also. See, when the point is on the axial line, suppose here is this point P dash. So what will happen? The angle between this R and this P vector will be 0, right? Isn't it?
Yeah.
And hence this will become cos 0, which is 1. So the formula reduces to the first one, which is for the axial point, right? And if you want to find the
Yeah.
potential at equatorial, the angle between this R and P will become 90. So cos 90 is 0. That will become 0. All everything, right? So this can be used to find the form potential at any point.
Yeah.
Now we can just write a point. So this potential due to a dipole is spherically symmetric. Note it. Oh, I'm sorry, it's not spherical. Potential due to dipole is cylindrically symmetric. Okay, this is an important observation. You can write it. Why this is so?
Okay.
See, if we
Uh.
if we rotate the point P about the dipole axis, okay,
Yeah.
then the potential will not change. Where is this P? Any P you can take. Suppose you take this P on the axial point, okay. If you rotate it, like you make a
Okay.
cylinder out of it, you know what I'm saying. Suppose mm, okay, you do. Okay, so this is the center, let's say. you make a cylinder like this. Okay, this point is on the surface
Yeah.
of the cylinder, right? Now if you rotate
Yeah.
this point along this cylinder, along the surface of this cylinder, along the line, axial line, right?
Yeah.
The potential will not change. That's
Yeah.
what it means by cylindrically
Okay.
symmetric. So we need to rotate the point P along about the dipole axis, but keeping r and theta fixed, because if we change the theta, that means the angle between the P vector
Yeah.
and the r vector. That means if we take this point somewhere here, that won't hold true. The cylindrically symmetric thing won't hold true. This r has to be same, and the angle, that means this point can be rotated like this on the surface of the cylinder, you know.
Yeah.
Okay, so this is what it is. Now let's find the potential due to a system of charges. Potential due to
Okay, can you make charger, please?
larger. Cannot you see this?
No, I said I need to go get my charger.
Okay, okay.
No, I said I need to go get my charger.
All right. Okay. So let us find the potential due to a system of charges. System of charges means that various charges are put in space. Q1, Q2, Q3 might be somewhere here, and we want to find the potential due to all of these charges. It may go up to n, right? We want to find potential at some point, any point. Let's say this point P. Okay. So what do?
Yeah.
We first, what we do is we will draw vectors from each one of these charges to this point P. So this is R1,
Okay.
R2, R3. Now just simply find the potential due to each one of these charges at P. So V1 due to Q1 is 1 by 4 pi epsilon naught, Q1 by R. V2 would be 1 by 4 pi epsilon naught, Q2 by R. V3 would be 1 by 4 pi epsilon naught, Q3 by R. And the total potential will be just the summation of the three, because they are, each one of them is a scalar, right? Don't need to take care of the direction, you just simply add them, right? Okay,
Yeah.
so this is very simple, isn't it? Now if there are n charges, the summation will go from 1 to n. That's it, nothing special, right? Next we will find,
Yeah.
this is done. Okay, so next find We find the potential due to thin spherical shell. See, the things we are finding the electric field for, the same we are doing for potential. Okay, we started from point charge,
Potential.
then dipole,
Yeah.
then the system of charges, then this spherical
Yeah.
shell. Alright, so there will be three cases again for the spherical shell. One, when the point P lies outside. First will be when point P, where we want to find the potential at, it lies outside the sphere. Okay, this is the first case.
Mm.
Now what will happen for the first case? You know, I told you that while finding electric field due to a thin spherical shell, we found out that E was similar to as that of a point charge,
Yeah.
isn't it? As if all of the
Yeah.
charge is concentrated at the center. The same thing goes here, because since it is appearing as a point charge for a point outside the sphere, so the potential will also be as that of a point charge, 1 by 4 pi epsilon naught q by r, if a point lies outside, right? Okay, so the sphere, suppose this is the sphere, this is its radius capital R. We want to find the potential at a distance r from the center. So this whole sphere will behave as that of a point charge whose all charges at the center q charge, right? Now second case, when point lies on the sphere itself. Okay, and the point lies on the sphere, what will happen in this case? Everything else remains same except that this r will be changed to capital R, isn't it? Because this will still behaving as a point charge. So capital R. Now the third case, when P lies inside, what will happen when P lies inside?
Yeah.
What should happen? See, the electric field is 0 inside the shell, we know that, right?
And the inside is here, but
Inside the whole shell it is 0. So when there is a general rule you can remember, right? When there is equal electric field or constant electric field, okay, so the electric potential will be the same everywhere inside that region. So E is 0 inside this region, right? E is 0 here, E is 0 at any point inside the shell. E is 0, we derived it, right?
right this now.
We derived it.
Yeah.
Now when E is 0 at any point, that means this is constant, okay? And when E is constant, so the potential will be the same, potential will be uniform, V will be uniform or constant.
Yeah.
So electric potential due to a uniformly charged spherical shell is constant inside the shell, and its value will be as that of a on the surface.
Okay, whole surface.
Yeah, that was on the surface. The same electric potential will be at any point inside it. All right.
Okay.
Yes.
Yeah.
So finally we draw the graph. If you want to draw the graph, how will the graph look like? Suppose this is a shell.
The same as an electric field.
No, electric field was zero, no, inside. But this potential is not zero. This is equal to this.
Alright. Yeah.
So how will you draw? See, mm, at the surface,
So the electric potential will be constant.
let's say this is some potential V inside, and this will be the same at every point until we reach the point outside the sphere, right? It will be same constant as we move on along the radius. It will be some fixed V, which will be this. Okay, this is not changing along X.
Yeah.
As soon as we move to a point which is greater than the circumference, it will vary inversely with R, right? Because it is the same as that of a point charge.
Yeah.
So this will be the graph, right? This will the graph look like. So at this point, what happened? Just a second.
Um.
So this here V is proportional to 1 by R. Here V is this 1 by 4 pi epsilon naught q by R. This is the center of the sphere. You can just write it as R, not X. Okay. Should we move on?
Yeah.
Now let us do some questions.
Yeah.
So let me copy this. You can look at example 1 on 2.5.
Okay.
Not able to copy. If 100 joule of work is done in moving an electric charge for coulomb from one place where potential is minus 10 to another place where potential is V, find the value of V. This is the question. There is some point, there is another point. Okay, now 100 joules of work is done in moving a 4 coulomb charge this was 4 coulomb charge and 100 joule of work is done. So W, suppose this is A, this is B. We have moved it from A to B, so WAB is what? 100 joules, right? And the charge is 4 coulombs. Potential at this point is what? Is minus 10 volt, right?
Where's 100 joules?
100 joules is the amount of work done in moving a charge Q from A to B. Right.
Why did it say 18?
What are you saying?
Where? It's not even. It says 18.
I'm saying on page 6.2.5. Just after the
Example
spherical
1?
shell. Yes, example 1.
Yeah, so it says the work done in moving a charge of 3 coulomb from a point A, which is at potential of minus 2 volt,
Where
to
are you?
another point B,
It is page
is 18 joules.
page 5 in the book. Like the PDF page is 5.
I'm looking at my book.
No, I'm
Isn't
using
there other question?
using the PDF version.
No, I'm looking at the hard copy which I bought.
Oh, okay, this must be different. Actually, I'm not able to copy it right now. Let me try it one more time if I can. Okay. This is 100 joule of work in moving a charge 4 coulomb from A to B. And the potential of this point is VA, which is minus 10 volt, right? We need to find the potential of this point. So how do we do this? We will use the potential work relation. What is the potential work relation? Potential work relation is VB.
Wait. It is work done on charge.
In terms of A and B. Okay. What will be? So VB minus VA will be what?
VB minus
WAB by Q.
Potential difference. Yeah.
Right?
Yeah.
Now you just substitute the values. That's it.
So VB minus 10.
Yeah.
Is equal to 100 upon 4.
Yes.
So V is 15 volts.
It's 15.
Now 15.
That's the answer. Okay. Let us see example 5. What is that?
Electric field intensity at point B due to a charge Q kept at a point A is 500 per coulomb, and the electric potential at point B due to some charge is 12. Look at the distance A to the right charge.
Yes. See, we are given electric field intensity at some point B due to a charge Q kept at point A. For example, it can be like this. due to a charge at A, the electric field intensity at some point B is how much?
No, the electric field intensity at point B to the is 12 Newton per coulomb. 24.
24. Okay. 24. There is some charge at A, due to which we already know that there will be some electric field due to this. So at this point B, this is what the electric field is, the magnitude of that electric field. Now further he's saying that electric potential at B due to the same charge is 12. So E at B is 12 and V at B due to the same charge is 12. Okay, joule per coulomb, right?
Yeah.
We want to find the distance AB and the magnitude of the charge. See, you will be needing to apply both the formulas. First one is for that of electric field due to the point charge at A, and then the potential due to the charge. So what is the electric field? K Q by R square, if this is the R distance.
Yeah.
And what is V? KQ by R. Now the catch here is that we don't know the Q, we don't know the R, so we cannot use individual formulas to find R, right? Because if we substitute E here, neither you know Q nor you know this R, right? That way it cannot be solved.
No.
How it can be solved is that you can divide these equations. This is first,
Okay.
this is second. Divide first by 2 or 2 by first, whatever you do. So E by V will be what? Here you will have KQ by R square divided by KQ by R.
KQ by R.
This KQ gets cancelled.
Should be R, yes.
E by V will be what?
R also.
R by R square.
Yeah.
Because this is 1 by R square. 1 by R square into you will get R. Because that's divided by 1 by R. This is divided by 1 by R, right? This is the whole fraction.
Yeah.
So you will get R by R square. This gets cancelled. So E by V will be what? 1 by R. Now you know E, you know V. You can substitute it here. E is 24, V is 12. So you substitute that. 24 by 12. 24 by 12 is 1 by R. 12 to the 24. R is 0.5. Right?
Yeah.
We have found the distance AB, which is R. Isn't it? The first part is done. Now we want to find the magnitude of this charge Q which was put at A. I mean, we need to find this Q, small q. So we can just now simply do that by using either one of these equations now, because we know R. So why not use this, because this is R, not R square. So V is 12, K is, let's say, be K, Q we don't know, R is 0.5. Sorry, this is 0.5, not 0.25. Q will be 12 5 is 60 and 60 point before 1, so 6K, right? If you cross multiply. Now you can simplify it. I don't know what is the answer. 6K is the answer. It will be some 0.667 into 10 to the power minus 9. Okay. All right. This is a good question. Example 9. Can you see the example 9?
Yeah, there's 2 chargers, 3 in the direction power minus 8 coulomb and 2 minus 2 in the direction power minus 8 coulomb or in K50 centimeter power. That one?
Yeah, that one.
Okay.
Example 9. Two charges are there, I think, right?
Yeah.
One of them is 3 into 10 to the power minus 8. So Q1, let's say it be Q1. And the other charge is Q2, let's say, which is minus 2.
Interest from 2.
And the distance between them is not given. Oh no, it's given 15. So the distance between them is 15, right?
Yeah.
This is 15. What he asked is, at what point on the line joining the two charges is the electric potential 0? Okay.
Yeah.
What he's saying is there is some point P in the line in this line. Let's say this is, don't take in the middle because we don't know where is that
Okay.
point. Okay. We will take it as a distance of x from one of the charges. Okay.
Okay.
And the rest of this
Yeah.
will then be 15 minus x because the whole length is 15.
Yeah. Yeah.
We need to find this distance x where this potential will be 0. Now when will the potential be 0? When the potential due to charge q1 at point P plus the potential due to q2 at point P, that sums up to 0, right?
Yeah.
So it will happen when v1 plus v2 becomes 0 at point P.
Okay.
Now you did use this equation and then substitute the values. So what will the b1 be? 1 by 4 pi epsilon naught q by r, which is q by r, which is x, plus 1 by 4 pi epsilon naught q, which is minus 2 into 10 to the power minus 8, divided by r, which is 15 minus x. Okay, and we should not write it 15 minus x because that is 15 centimeter, 0.15 minus x. We need to change it to meters, right?
Yeah.
This sums up to 0. Now just solve this. So you know what, this will get cancelled out because we can take out this common and then it would become 0 on the other end. Okay, so we are left with this 3 into 10 to the power minus 8 by x. It will be equal to minus, it will go on here, if this goes on here this will become plus, right? You getting it? Oh, this is minus, so this will get cancelled out. Now you cross multiply, so 3 into 0.15, 15 is a 45, 4.5 minus 3x equals to 2x, and if you take this on here, 5x.
Yeah.
So what will x be? want to change it to centimeters, you can multiply it by 100. Okay, so 5 to the 10 0,
Oh,
and 4.5 into 2 will be 9, so 9. No, for this is 4.5 into 20, so this will get cancelled with this 90. Oh, it should be 9 na, not 90. Okay, let us see example 14. You just see it in the book. Where are you? I cannot hear you.
yeah.
So two charges of minus q and plus q are located at A and B. Can you see? Example 14, A and B are the 2 points. How much work is done in moving a test charge from point P700 to this Q minus 300? So this is question is somewhat confusing, but it is very easy. There is nothing to worry about these coordinates. See this is a minus q charge, this is a plus q charge, so this means they constitute a dipole, right? Hello.
Yeah.
So they are, no, I cannot because you're speaking very low.
Is this better?
No, this is not better. No.
I don't know what's wrong.
Anyway, you see the book.
Okay.
So he is asking about the work done in moving this charge from P to Q. Now this P to Q is
Yeah.
lying on equatorial line of the dipole. Okay, and we know that the potential at equatorial line is what? It's zero on the, so when the potential is zero on this line, then we can simply move a test charge from P to Q without doing any work, because the charge is zero at any point, so that is why the work done would be zero.